I want to do some digital logic gate circuits, so digging into my big pile of tubes of digital logic, I'm going to use the 74HC132 quad 2-input NAND gate with Schmitt Trigger inputs. So the NAND gates have that Schmitt Trigger symbol on it. What is a Schmitt Trigger? Well, we're not going to go deep diving into it, but we will say it is a circuit configuration that adds hysteresis. So when you have a certain output based on a certain input, the output value is not going to change until the input has changed enough to trigger that new output state. This transfer function here shows how the output on the y-axis responds as the input on the x-axis changes between a lower threshold voltage and an upper threshold voltage. The input 0 volts may be on the left here and 5 volts may be on the right, and these two thresholds, in the case of this logic gate, the high threshold at close to 5 volts VCC may be around 2.7 volts, and the low threshold may be around 1.6 volts. 1.6 volts, 2.7 volts. So this symbol in the Schmitt trigger looks like this transfer function shape. What this diagram represents is if we have an input that starts at 0 volts and it's going to rise up toward 5 volts, the output voltage on this Schmitt trigger is going to be at this certain threshold here all the time until the input reaches this upper threshold. When it does, it triggers a change of state, so now the output immediately switches to this other level. And while it's in this zone, if the voltage happens to be still rising and it's noisy and it's flipping around, say 2.7 volts, 2.8, 2.5, back to 2.7, on a regular gate, that may keep triggering high-low outputs. Since we are latched into this threshold now, in order to trigger this output to change back, we have to have this input voltage fall all the way back to this lower threshold, 1 point something. Then the output will switch again. And when it's in this state, again, if we have a changing signal, but it's not changing enough to go all the way to this upper trigger, this is just going to stay in this state. When you have a genuine change of state from low to high again, finally you get an input high enough to bring this to the other state on the output. So this basically gives you noise immunity. And I took some scope captures to illustrate this diagram here, comparing a regular gate and a Schmitt trigger gate with a noisy input. So on a regular gate with no Schmitt trigger inputs, if you switch the input high to low relatively quickly, the output looks relatively clean as well. But if you're transitioning slowly and you have noise, you may get all these false triggers. And actually, if you're rising or falling so slow that you're kind of lingering in an indeterminate state, your output may not be high or low. It's in the middle somewhere. So if we have a slow moving signal, we can get better performance out of a Schmitt trigger. So with the Schmitt trigger, once we go high enough or low enough to trigger a threshold, the output will change, but then it won't change again until we get far enough in the other direction to trigger it again. So it's a moving target to actually trigger this gate to change its output between high and low. And if you have some noise, it basically gets filtered out. So Schmitt trigger inputs clean up noisy signals. So skipping ahead in Schmitt trigger application usage, if we have a single Schmitt triggered inverter, we can make an oscillator just with an RC timing network. Since the output is always going to be the opposite of the input, let's say the output is high. Well, now this capacitor to ground is going to charge through this output plus V at a certain RC time constant. And when this charges up high enough, this Schmitt trigger input is going to see a logic high in, and it's going to invert to a logic low out. So now the output, being logic low, is going to sink current through this resistor and discharge the capacitor. When this voltage here gets low enough, the input of the Schmitt trigger is going to see a logic low, switch the output to a logic high, and again source current to charge the capacitor through this RC network. So you end up with an oscillator. The capacitor is going to discharge down to the Schmitt trigger's low threshold, then start charging up to the Schmitt trigger's high threshold, and so on. and you're going to get a sharp logic output, high and low, at whatever high and low voltages this gate can drive, close to VCC and close to ground in the case of a 7.4HC CMOS inverter. Since I'm working with NAND gates, if I tie the two inputs of a NAND gate together, that's an inverter. So I can use this as a Schmitt triggered inverter. When I tie these together, if both are low, we get a high. If both are high, we get a low. The frequency of the oscillator is primarily determined by the RC timing network, plus a small propagation delay through the gate. When you switch from low to high, high to low, it'll take a very short time to get through the gate and switch this output. So we determine how long it takes the capacitor to discharge and how long it takes to charge. That's the period, and 1/period is our frequency. There's lots of resources about calculating charge and discharge voltage of a capacitor, but I found this resource, and they have a PDF about time constant calculations. So when I open this, it's Creative Commons, so we can look through this. There's sites out there that derive this kind of thing all the way back from Kirchhoff's laws, so we're just going to look at this as our final equation that we can use to calculate charging or discharging. So in the end, we know everything here in our case except t, the time. We know the RC values for the RC time constant. We know that our ultimate final voltage, if we let it keep charging or discharging, is either going to be close to 5 volts or close to ground. And we know the target voltage we're looking for and the starting voltage we're going from. Those are the lower and upper threshold voltages of the hysteresis. If we start right here, we know the voltage here. It's whatever that lower threshold is on our gate. We know our target is going to be whatever the upper threshold is on the gate. We know that if we let it keep going, it gets to whatever the gate can output close to VCC or discharging. We know if we let it keep going, it would try to get to whatever logic low is close to ground. What we don't know is what's the time it takes to discharge or the time it takes to charge. So we use this equation, solve for that time for both charging and discharging, add those together, and that will give us the period of our signal. Then 1/that gives us our frequency. I found this online calculator that uses the same parameters. If you're looking for any one of these, you enter in all the others and it will calculate what you're missing. From voltage is the initial voltage on the capacitor. Say we're charging up, the initial voltage is this right here. The to voltage, what you're actually charging or discharging toward. So the to voltage is up here if we are charging. What they call supply voltage, the voltage that you will eventually get to if you let this keep charging or discharging. So they just call it power supply voltage, assuming you will get all the way up to VCC. But if you're discharging, you would put it to 0, and that's the same as having a short circuit across here, and you're just discharging the capacitor. And you know your capacitor and you know your resistor, so you can solve for time. I constructed this circuit using the Schmitt Trigger input NAND gates as an inverter. This is a 100K resistor, but I wrote in 97.8 just as a reminder because that's what I actually measured. And this was a 10 nano capacitor, but it measured 9.1. So I simulated this, although this is not giving me my exact frequency because the frequency depends on the upper and lower threshold voltages. And this simulation has certain presets in there, so my actual circuit is going to be different. So it's going to charge or discharge at a different time and have a different frequency, but this is just to show the circuit. So let's go see this circuit in operation. Here's the Schmitt Trigger inverter. I have a green LED here blinking. It's set for 1 Hertz. There's a potentiometer here to adjust the frequency, and there's currently a 1 micro capacitor. When I increase the frequency, I want to use a speaker output as well to hear it, so I built a tiny NPN transistor driver because the output of the logic gate is not enough to drive the speaker directly. So it looks something like this. The output of the inverter oscillator goes to a base resistor and an NPN transistor, emitter to ground, and then a speaker in line with 5 volts. So now as the oscillations occur here, it turns the transistor on and off and generates sound. This is a 1 meg pot and it's currently set at 956K. The blue channel 2 trace is the output frequency and it is 1 Hertz, 990 millihertz. The yellow channel 1 triangle is the charging and discharging of the capacitor. so it's easier to see the LED blinking at this rate when it's darker. So as I increase the potentiometer, the blinking and the frequency are increasing. So I can get up to about 25 Hertz with this 1 meg pot and 1 micro capacitor. Now I swapped out the capacitor for a 10 nano. With a 1 meg pot, the lowest frequency I get now is 100 Hertz instead of 1 Hertz. Now if I connect a speaker to that little transistor driver, I'm able to get it to go up around 4 kilohertz with these component values. Now coming back to this capacitor charge and discharge calculator to compare against the real circuit. So after looking at my circuit's real behavior, my frequency is 1.064 kilohertz. I've zoomed these in, these are not to scale, so this triangular wave is the capacitor charging and discharging to the Schmitt Trigger input high and low thresholds. So the upper threshold is 2.91 volts, the lower threshold is 1.73 volts, so that's how high and low this capacitor is charging and discharging. My output that the gate is capable of driving, the typical high voltage aside from any noise, is 4.78 volts, and my low is only 45.6 millivolts. So I've imported these values along with my measured capacitor and resistor values, and it tells me it's 435 microseconds to charge that capacitor. So that's part of the period of my output signal. So we're charging from 1.73 up to 2.91. If we let it keep going forever, we could get as high as 4.78, that's what the gate is capable of driving. And when we are discharging, we start at 2.91, we're discharging down to 1.73. If we let it keep discharging, the gate is capable of bringing it down to 45.6 millivolts, and this takes 472 microseconds to discharge. So we add 472 microseconds plus 435 microseconds, and then that's the period. So 1 over that. So our calculated frequency using our real circuit parameters is 1.1 kilohertz compared to the actual measured 1.06 kilohertz. So it's a 3.5% difference, which I think is pretty good. So now what we can do, we can start using more oscillators and more logic gates and just get creative. So this is just a simple example. I've now taken the same circuit and duplicated it, changed one of the part values to give me a different frequency. So oscillator 1 is oscillating more slowly at the top waveform. Oscillator 2 is at a higher frequency. And now I've Nanded these together to create a unique output waveform on the bottom. So because of the way a NAND works, let's say we keep one input always low, right here. Well, no matter what we do on the other input, high or low, the output is going to be stuck high, so that's not what we want. But if we take one input and tie it high, then the output will change as the input changes, although it'll be the opposite because it is an inverting gate. We can use this functionality to gate one signal with another. So what this circuit is doing, this slower oscillator is enabling or disabling the faster oscillator to pass through. When this slow oscillator is high, the second oscillator, high and low, passes through, although it's inverted. But it doesn't really matter, it's the same frequency. When the first oscillator is low, it just keeps the output latched at a 1. So if these are slow-moving oscillators, we could have this set to blink an LED a couple of times and then pause and then blink a couple of times and so on, similar to maybe a lighthouse or something. Or if this is fast enough into the audio frequencies, we can have a single tone and then gate it on and off, so you end up with a sort of a beeping tone. It makes a tone, it stops, it makes the tone, it stops. And if you change all of these parameters, you can generate some interesting effects out of this. It's just a simple concept demonstration, so let's take a look at how this circuit works. Now I have a whole lot of stuff hooked up. I made 2 Schmitt Trigger inverter oscillators. and I can adjust the frequency independently with two potentiometers. And on the output of each oscillator, I have an LED, so the frequencies are set relatively low. We have a fast blinking LED and a slower blinking LED. Then there's a third LED connected to another NAND gate, where input 1 is a fast oscillator and input 2 is a slower oscillator. So it ends up giving a blink pattern that's gated. So you get a few flashes at the rate of the first oscillator only when the second oscillator is either high or low, depending if you're inverting things or not. So it turns out when it's low, it enables the blinking. So it's easier to see when it's a little darker. I only have a 2-channel scope, so we have the faster oscillator on the top, representing the faster blinking light, the slower oscillator on the bottom, representing the slower blinking red light. So I'll take the top channel and put it on this output third LED. So on the bottom trace we have the red LED's oscillator, so this output LED on the top trace. So that can allow you to sort of generate custom intervals or waveform patterns. But if you connect up a speaker and make a faster oscillator, so I kept the blue trace as a slow oscillator to gate another oscillator now with a higher frequency. I switched out capacitors. So now the final gated output waveform is a higher frequency audio tone only enabled when the slow oscillator allows. So if I hook up the speaker and play around with both the tone and the gating speed, now moving forward, if we were to take this fundamental concept here and expand on it and maybe gate some other signals and maybe make them not exactly straightforward oscillators, maybe we can generate even more interesting waveforms, including audio sound effects, or even simulate musical instruments. I'll carry this concept forward in future videos.